This is today our technically speaking last session, but it's a back-to-back. This is going to be hosted by Dr. Murat Sarihan, who is one of our own. He did his PhD at UCLA, and he's going to talk to you about designing a small-scale device with Qiskit metal. We're actually going to use Qiskit metal and Palace and SQD metal. And yeah, he's going to walk you through it, and don't you worry, everything is very well documented. If you have questions, just feel free to ask, right? I'm here, and obviously also for people online. Yeah, and then please welcome our speaker.
Thanks for the kind introduction. My name is Murat. I'm currently working as a research scientist at Google Quantum AI. So also I'm one of the organizers of this workshop, and I would like to cheer for this beautiful team of UCLA students here. That they really did most of the work, and hope we would like to continue with great feedback from you. And next year, we are also looking forward to having you here again. So today, so for the last 2 days, I know it was pretty hectic, pretty full, a lot of great talks about the fundamentals of superconducting devices, what is a transpond, how can we understand what is going on during a quantum operation, and we have some introduction towards design concerns and how we can do design. The aim of this workshop is to introduce you, actually, we have all these tools, different formulas about transpond Hamiltonian, dispersive shifts, everything. I would like to establish a mind map today so that you can have an idea about where to start, how you can flow, and at the end, how you can reach a desirable device that you want to use for your research or even for your job. So at this, we would like to have a basic idea of that here so that you can implement more complex designs in your future actual endeavors. So for this purpose, we will be using Qiskit metal for device design purposes to draw our layout, to determine qubit parameters. We will be, for EM simulations, which is the cornerstone of this quantum device design, we will be using an open source package called Palace. I know both in person and online, some of you might have problems installing that. It's a little bit of a tricky package, but even though you couldn't install that, it is okay. Actually, this workshop won't require you to simulate complex devices. Anyways, having a full-scale EM simulation for accurate results would require actually half an hour per simulation, and we don't have that much time. But I seriously encourage you to use this tool in a good computer and simulate your designs with high convergence to see what you can get out of that. So I will be walking you through with how do we design our devices in Qiskit metal, how we can integrate that design into Palace environment by using another open source package called SQD metal. It's a wrapper around Qiskit metal that is used to bridge these two tools. Normally, the Qiskit metal is mainly working main interface with the HFSS, which is industry standard for EM simulations, but it is also behind the paywall. And unfortunately, we couldn't have servers that can give access to all of our attendees, so we apologize for that. And also, Zlatko promised me by next year, we will have a much better open source solver integration into Qiskit metal. So you will have a much better actual idea in your research. So without further ado, let's start. By the way, if you have any questions about reaching to this notebook, I put the link for the GitHub in the chat, and I think also the organizers put this Python notebook inside a folder for the materials.
So it should be on Google Drive. Yeah, I can also send it in Discord, but you should all have it there. It's called Murat slides or workshop.
No, I only see the ABCD file.
Yeah.
Could you double check that before we started at this stage?
I see the new file. I mean, so if you go on workshops, it should say Murat, Jens Koch, and ABCD.
Yeah, it's there.
Same thing.
Also online. So if you go on a Google Drive, there should be 3 folders for 3 different workshops so far.
So also at the beginning and end of this Python notebook, we put some resources. Both at the end, we have some references about the fundamental review articles and the seminal papers on this field, including the Koch et al. 2007. We have some document links for Qiskit metal and some videos previously prepared by Zlatko and IBM team on Qiskit metal to draw more complex designs. And also the squads database, which is being developed by Eli Koch and Salman Shamto, who are also our organizers. And also the SQD metal page have more resources about how you can effectively control and play with your parameters in this simulation package. So without further ado, so here we have some import links related to the Qiskit metal components, mods, and basic NumPy tools. So the first thing, in order to get it run, you need to define your path to Palace, the link for your Palace executable in your computer, in order to be able to run the simulations here. So now let's start to discuss about what a small-scale single qubit system looks like in order to be able to effectively control and read out a transmon qubit. So we can analyze most of these quantum superconducting devices in terms of lumped circuit elements, where during this workshop, we talked about how we can model transmon as a weakly anharmonic oscillator, which has a shunt capacitance and Josephson inductance, which has a inductance dependent on state, which gives you that anharmonicity. You have another LC resonator here, which corresponds to our resonator. In this circuit, which is the most common, we decided to couple our resonator to qubit using a coupling capacitance here. And also, in order to effectively do single qubit rotations, we started with adding a voltage source here, also connected by another gate capacitance. This is often called in literature as charge line, and this is used to control the state of our transmon qubit. So this was discussed by multiple people during the workshop. The Hamiltonian of our transmon looks like this. It has a capacitive energy component, depends on the charge operators, and the cosine cosine flux operator here, which is the energy of our Josephson junction here. So the shunt capacitance for here for our qubit, it is not just the capacitance of the block shunting the Josephson junction here, but it also includes the capacitance that's formed on Josephson junction, which alters your resonant frequencies a lot if you don't include that as well. And also, if there are any coupling capacitances seen by this Josephson junction here, those are also affecting your effective capacitive energy seen by your Josephson junction. Thus, your qubit frequency will be depending on your Josephson energy and inductance of this Josephson junction here, but also the capacitances that are connected to this Josephson junction as well. So that's why we call that as the sum of the capacitances. And also, I don't want to go into detail for this, but for the scope of this transform analysis, we will be working on the charge basis. So we converted this cosine phi operator here and discussed that in terms of the charge, its charge equivalent. And as you see, the n+1 here, as Professor Koch just showed, shows the transition between different charge states. So the first thing you need to be sure in order to design a transmon qubit is looking at determining your EJ, your Josephson energy, and your capacitive energy of your system. This determines the main operating frequency of your qubit, but also affects your other properties as well. So one of the most important things in designing transmon qubits are the charge dispersion. And here, you need to be careful that your transmon qubit is not susceptible to any charge noise fluctuation. So normally, our transmon Hamiltonian is dependent on a gate charge we call, and we use that also to control our transmon state. But in the case of overall charge qubits, this gate charge here is also corresponding to all fluctuations and charge noise that's entering into your system. So in order to avoid effects of charge noise, we are using a larger shunting capacitance compared to our Josephson junction. And the ratio of that capacitance to your Josephson energy is very important in order to have a high coherence transmon qubit. So you can simulate the effects of charge dispersion on your qubit by using either, there's a package called, there's a class called HCPP. It corresponds to Hamiltonian Cooper-Bear Fox class within Qiskit metal. Or you can use, we just learned about the SC qubits package. You can also use SC qubits to model your Hamiltonian of your transmon and get an estimate about how the charge dispersion picture looks like for your qubit. So here, we assume our charging energy is equal to 220 megahertz as an acceptable value, which is common in transmon qubits. And we pair them with different Josephson energies. It's the 1 times, 10 times, and 50 times of the charging energy of the qubit. And we looked at how our charge dispersion picture looks like. So as we see, and here the y-axis is normalized by the qubit frequency, so that normally for different EJs, your the qubit frequency will be different. So here, that's why we normalize our energy eigenvalues to the qubit transition frequency, qubit transition at hot flux. And we looked at different ratios. And as a rule of thumb, as you see here, for different gate charges, at different energy levels, you can see a drastic change in your transition frequency. And during your qubit operation, if your EJ over EC ratio is very low, what you will end up is any charge fluctuation, any noise in your system will cause your qubit frequency to change. And qubit frequency changing means actually your qubit undergoes dephasing, will acquire different phases that will destroy your quantum information. So as a rule of thumb, mostly we are looking at, in transmon region, we are looking at EJ over EC ratios minimum at 30, preferably actually 50 or above, so that you can have a very flat charge dispersion figure compared to your gate charges, and you can eliminate one form of decoherence channel for your transmon qubit. Of course, we don't just have the charge variable in this transmon qubits, we also have a flux noise. So at the expense of flux noise here, actually we are avoiding the effects of charges. So here we also did the same thing for a continuous. Yeah, we also did a sweep of the epsilon, which is the charge dispersion, the change in frequency versus your gate charge. And we select that for different EJ over EC ratios. And you can see how exponentially it scales with your different EJ over EC ratio. So here, 30 corresponds to for different energy levels. So for our qubits, we are mainly concerned about 0 and 1 states. But for some applications and also for leakage and other considerations, your higher order state dispersion is also important. So they have different scales for charge dispersion. For the ground state, what we have here is at 30, we have almost around less than 10 over minus 4, and around 50, our charge dispersion, the change in frequency with the charge is less than 10 over minus 6. Yes.
Can you elaborate on the trade-off between the flux noise and the charge noise?
Yeah. So flux noise is always present there due to the magnetic vortices around or your like a control line currents changing your quantum state. I will show you one plot on that about the eigenfunction atomic loop side. But especially flux noise is much dominant when you have a tunable qubit, for example, that has a special flux control line. So for this kind of single junction transmodes, we don't have any flux tunability. So there will be, of course, a flux induced dephasing on your system, but it won't be as drastic for fixed frequency qubits compared to flux tunable qubits, because we are basically operating them at around zero flux. But we will see that for state-of-the-art implementations, most of the groups are right now using tunable transmodes, which you can tune the frequency of your qubit in order to find the sweet spots that are insensitive to flux, in order to determine your interaction frequencies, and also in order to avoid this what is called two-level systems present in your device that can interact with your qubit. Sometimes the material itself has some two-level systems which are also like have their own coherence properties. They are like artificial atoms. They might interact with your qubits, so you may want to have a tunable qubit in order to avoid that as well. And for them, since we are operating them at different flux modes, the flux noise is mainly actually proportional to the amount of flux present in your system. So that will be more important than flux tunable qubits. At least here, we are trying to mitigate the charge noise, and flux noise, we are operating at a regime that is less effective on our qubit. Any other questions so far? Okay. So here, in order to determine our qubit parameters, I also use SC qubits as a handy package. Here, my target was having a qubit with frequency around 5 gigahertz and with a EJ over EC ratio over 50, and have an appropriate unharmonicity for my device. So here the values I used was for Josephson energy, I used the value of 18 gigahertz. For EC, I selected it as 180 megahertz so that I have 100 of EJ over EC ratio, and simulated these parameters in order to get my qubit frequency and the unharmonicity. So there are some trade-offs here. Of course, your qubit frequency is determined by, we saw the formula is square root of 8 times EJ over EJ times EC minus EC. So both EJ and EC increases your qubit frequency. But if you increase both, you would end up having a very low EJ over EC ratio, which increases your charge noise susceptibility. So you don't want that. So that's why we try to keep EJ over EC ratio as high as possible. On the other hand, for a given frequency, let's say you want to increase your EJ as much as possible, you need to keep your EC low in order to have the same, let's say, 5 gigahertz frequency. So what you end up doing is, you need to also have an appropriate EC here, so that your qubit is reasonably unharmonic. The reason for that is the weak unharmonicity of our qubit helps us distinguish different transitions inside our qubit. So normally for a regular LC resonator, all the energy transitions will have the same frequency. From 0 to 1, 1 to 2, 2 to 3, they would be all having the same energy. Without any unharmonicity, we would not be able to control our qubit and just target the transition between 0 to 1. So the unharmonicity we have here is actually helps us distinguish between different transitions of the qubit, 0 to 1, 1 to 2, 2 to 3. And if you have enough unharmonicity, you can, with higher precision, you can control your 0-1 transition well, so that you don't have to worry about the concept of leakage, where your qubit transition, your qubit state goes into some non-computational state 2 or 3. Because when we are controlling these qubits, we are sending a pulse centered around the center frequency. And our gate length, in order to do a fast control on our qubit, it has a trade-off with its spectrum in frequency space. So we know from Fourier transform that shorter is your gate pulse, your frequency uncertainty would be larger. And if your gate is shorter enough, when your frequency uncertainty is larger than your unharmonicity, your pulse that you send would start exciting other states as well. And that would cause lose of ecoherence in your system.
Question from online. Why do we want EJ/EC to be as high as possible here compared to earlier, where charge dispersion, where we notice a loss in qubit data when the duration is higher? Apparently you said it has to be as high as possible.
EJ or EC ratio in order to avoid charging. So that's EJ over EC ratio in order to operate a transform regime and suppress the effects of charging. We would like to have as high EJ over EC ratio as possible, but there are limits for that. And those limits are namely your qubit frequency, if you want to operate at a particular target point, and also the unharmonicity that you have, which helps you distinguish between different transitions, so that you can effectively restrict your computational space into 0 and 1 transition if you have a high unharmonicity. And from there, you would be, so in most of actually theory papers that are discussing about transforms, they assume that our transform state is restricted between 0 and 1 state. So in order to have that, you need to have a decent enough unharmonicity.
So just to verify, does the EJ over EC ratio directly affects the unharmonicity?
Yeah. So in order to keep a high EJ over EC ratio, either you need to increase your EJ or decrease your EC. If you increase your EJ, if you want to keep your qubit operation frequency fixed, you need to reduce your EC as well. And when your EC is reduced, your unharmonicity drops. Otherwise, if you want to increase both, you need to operate at much higher frequencies. Let's say right now, the most of the qubits are operating between 4 to 8 gigahertz, for example. Even 8 is I think too much right now. This has both limits in terms of microwave control, the available electronics that we have, and also the practicality. If you want to operate with a frequency, let's say this is a 5 gigahertz is a decent frequency. In order to keep the ratio high, you need to suppress EC a bit as well. So you need to determine an appropriate EC that can help you to avoid leakage and keep your system in 0, 1. Okay. Okay, so now we set our qubit to have an EJ over EC ratio of 100. And let's have a look at how the wave function in charge and flux basis will go. So the first plot we have here has the matrix elements of our wave function in terms of different integers, actually gate charts. As we see here, our wave function over different charge basis states are highly delocalized. While when we look at our wave function in terms of a continuous basis of flux, this is a cosine phi. So here we put phi in terms of radians from minus pi to plus pi. As we see, we can see that in the local minimum in our potential valve, we see that our flux in the flux basis, our wave functions are highly contained. So again, using these parameters of 18 gigahertz and 180 megahertz of EJ with this EJ and EC, we also repeated our charge dispersion simulation using SC qubits. And as we see here at a very high ratio, EJ over EC ratio of 100, we see that there is virtually no charge dispersion in our energy diagram. So in this system, under the assumption of high EJ over EC ratio, it is given unharmonicity. We can identify our transport as a weakly unharmonic oscillator. And when we diagonalize our Hamiltonian, we can obtain our energy eigenstates in terms of ladder operators, B plus and B. Here, the B plus B operator is actually the number operator that shows you the number of photons present in your system. And with this slightly unharmonicity introducing this capacitive energy term. And as we see here, also this unharmonicity is mainly defined between the difference of 0 to 1 transition and 1 to 2 transition. And when you go up the higher states, actually, the spacing between different states are getting smaller and smaller. So your largest frequency transition of a qubit will be the 0 to 1 transition. And when you go down, it's going to be reduced. And as we discussed before, our qubit frequency, you can identify that as A times EC or EC times EJ minus EC. So the qubit frequency is both proportional to our EC and EJ. So in summary, we need to determine our EC and EJ according to desired qubit frequency. While doing that, we need to ensure their ratio is high enough to suppress the charge noise. And also, in order to have a better state distinguishability, and while doing fast control, we would like to have a high enough EC here to be able to distinguish between different. So as a result of this here, I used some Qiskit metal helper functions. This is CS from EC and IC from EJ, based on, because EJ and EC are very good in terms of identifying our Hamiltonian, but in actual device design, what we are working with is inductances and capacitance. So we converted these energies by using their appropriate formulas into the shunt capacitance and the junction inductance, and also junction inductance also related to the critical current that can pass through the junction. So in order to get 180 megahertz of EC, shunt capacitance we need is around 107 femtofarad. And the inductance, this is for a single transmon, single junction transmon. The junction inductance we need is around 9 nanohenry. And the EJ over EC ratio is around 100. So this holds for single junction qubits which have fixed frequencies. So I want to quickly touch to how the picture looks like in tunable transmon and why we need such devices. So for tunable transmons, in the transmon regime, where you have a high EJ over EC ratio, the Hamiltonian goes from EJ cos phi to this term, which has an extra square root of cosine squared plus d sine squared. And here you have another phi term, which is called phi external. In this case, how we design tunable transmons, we are using a superconducting circuit element called squids, which is basically a loop of two parallel Josephson junctions. And to that squid loop, we add an extra flux line to the system and induce magnetic fields that causes a circulation of a current inside the squid loop. And that, based on the external flux that you apply here, that changes the inductive energy of your Hamiltonian, of your qubit, which in turn which changes your effective frequency of your qubit. So by adding a second Josephson junction in parallel to the first one in your circuit, you can effectively control the frequency of your qubit. So here, D controls the asymmetry between two junctions. In this case, so you can have both of the junctions have the same inductance, so that you have a particular F max where it is determined by some of those two Josephson energies. But when these two junctions are symmetric to each other, your minimum energy is effectively zero. So that by controlling your external flux, you can completely turn off your qubit. And that can eliminate that qubit from your operation space, so that that qubit doesn't interact with other qubits in large-scale systems and don't cause harmful effects in terms of decoherence into your system. If you have a D not equal to zero here, which means D is defined here as the difference between two junction energies divided by the total junction energy. In this case, the asymmetry of D will cause different currents circulating at different branches of your squid loop. And at the end, your minimum frequency as a result of solving this, I will show now, it will give you a non-zero minimum frequency. So where that helps, if we use SC qubits again to simulate this tunable transmode and plot its energy eigenstates with respect to the external flux that we apply here, we see that the cosine and sine square terms there are causing the sinusoidal change in our energy eigenstate with respect to the external flux, And our maximum frequencies for each transition, these are higher order transitions, and this is the first order. Let's just check the first order one. At zero flux, we have the maximum qubit frequency here, and at the half flux point, 0.5 times the flux quanta, we have the minimum flux. Here, I set a D as junction asymmetry equals to 0.15. So here is our zero hertz energy eigenstate. So we see that actually the minimum of the qubit at the D level equals to 0.15 is above our 0 point. And it ends at here around 3 gigahertz also. The benefit of that is sometimes you want to add an asymmetry in order to reduce the change between maximum point and minimum point, which in fact reduces the derivative of this line here. And that derivative helps you to protect your qubit more from the flux noise while still retaining the ability to tune your frequency. So you can, by adjusting your D, you can actually both be able to tune your frequency and adjust the tunability range at the expense of your flux sensitivity. So that's something, depends on your system that you want to design, is important. So that you can trade off between tunability and the flux sensitivity. But at this point, we won't be able to completely turn off our qubit, so it will continue to interact with the neighboring qubit. Okay, so now let's look at how the capacitance simulation of our qubit looks like. So in order to determine the actual qubit parameters, we can use different methods. So for a single qubit, the most important parameter we have is the shunting capacitance in the isolated region, while the inductance that we have can be adjusted by in fabrication by choosing appropriate Josephson junction parameters. I don't want to go into detail much, but by changing the area of the Josephson junction and thickness of the barrier between them, you can easily adjust your Josephson inductance. But the capacitive elements of your circuit it's the main concern of you in your design, so that you can calculate only all the interactions, you can calculate all the resonant frequencies. So here we use SQD metal and the Qiskit metal. So as I mentioned, SQD metal is a wrapper on this to draw our qubit. So first in this code, we invoke a new design and open that up in our Qiskit metal graphical interface. This interface is a bit tricky. It doesn't really work in Mac computers. So I understand that, but I will be showing the screenshots coming from Qiskit metal itself. In Windows and Linux, I don't think there's a big problem about that. It has something to do with high QT packages. So we first define our design window here in terms of size X, size Y. I selected a small size of 2.4 millimeters. And I also determined the thickness of our substrate, which is here on the order of 280 micrometers. It's close to a 4-inch wafer thickness. And I defined, this is for the future, but I defined the coplanar waveguides we're going to use for buses, feed lines, and the resonators. I defined its width and gap. I will talk about that later. And then here, you have this in twisted metal as a function called transmon cross. And in HQD metal as a wrapper, you have a function called xmon to draw the transmon qubit for you. There are different, I did not put here, but there are different geometries you can use to realize your qubits. Mainly, those are divided into two. Either they consist of two paths, we call them floating transmons, where you mainly establish your capacitance of your qubit between two paths that are floating with respect to the ground element. And there is also single-ended or grounded qubits like xmons, where you have a single monolithic capacitive block of metal, which has a capacitance with the ground layer around that. And mainly the interaction between ground layers will determine the capacitance of your qubit. We also added a Josephson junction as a representation. And also we added a capacitor prong pin, it's a claw, in order to later hook up our resonators and other controllers. So after running this, so here for the transmon, initially I use, so I can first show how it looks like, maybe. I think this is small a bit. Maybe. Is it seen better? So this is what we call as an xmon or cross transmon structure, where you have a single monolithic layer of capacitor metal block, which is interacting with the ground layer around that and creates that capacitance shunting this junction here. As you see, the junction is also placed between this metal layer and also the ground around. So after this, we have this Palace interface provided by the HQD method. So normally Palace has a lot of options and have a different scripting where you save as a JSON file and push to Palace to do your simulations. So HQD method offers you a very nice wrapper for you to adjust your parameters. So here, mostly the parameters we are using involves how do we mesh and what are our solver tolerances. So here we set our dielectric material as silicon because in the EM simulation, the effective permittivity of your dielectric will be very important for your capacitances and also your qubit frequencies. You have the solver tolerance. Here we set it as 1e minus 8 and the number of maximum iterations. So it depends on the accuracy you want from your device. You would love to have this solver tolerances as small as possible. Of course, like it depends on your the computer power. Here we also selected the maximum element size of your mesh. So most of these EM solvers like HFSS or also Palace uses finite element method. So the size of the mesh elements are very important for the accuracy of your simulation. So we set the maximum mesh element size in terms of millimeters, so in terms of micrometers. And also we have the sampling rate. The fillet resolution is a parameter that controls, yeah.
I was just wondering if there is a minimum meshing dimension. And how that compares to hands.
So different devices, I think, have different tolerances for that. As far as I know, there is not much a well-established criterion for Palace, but what the values we are using are aligned with HFSS. At least I am trying to ensure that for every component I have, I can fit in at least 3 mesh elements inside the width of that particular element.
But is there a limit of the length scale that Alice can go to?
I don't think so, actually. It's a very strong solver with high performance computing elements. I think it's pretty strong about that. It's using Gmesh as the mesher. It's another open source package that does meshing. It doesn't do as great job as HFSS as far as I know for the meshing, but I was able to mesh even the junction sizes pretty well. So in this case, the values I use here are actually pretty broad, so that the simulation time is faster at the expense of accuracy. So we can look at actually how our mesh looks like here. In this, so here we need to initialize the meshing environment. So that's what I did. And then we move to the capacity, setting up the capacitive simulation, where basically you determine your directory to save these results, which meshing tool we're gonna use. There's also, I think, as far as I know, an alternative console-based meshing tool. And then, of course, here in this device, in Qiskit metal, we don't see the presence of metal around and extra metal. So it assumes around here, so the gray areas are your correspond to your substrate, where we etch the metal in order to create a gap between ground layer and the exmon. And here, these two codes assign the metal to your qubit area and also assign a ground plane around it. So after this, I would like to improve my meshing actually. So from Qiskit metal, I got this geometry bounds. That's the bounding box around our transmon, a square box around here. And I use those bounds here to mesh it finer with a resolution of 1 micron and with a maximum mesh of 50 micron here. Then you click the prepare simulation to create the Palace script that is used for this simulation. And when you use this display conductor indices, it gives you the order of elements in your resulting capacity matrix. Here, when we get our capacity matrix, it will show the interactions between these 3 different elements. So you have your transmon cross here, you have the ground layer around that, and you have that clone, the coupler we will use later for our resonance. And the order of that will be first, we will have first element will be the ground, then you will have the exmon and the clone. So then we run this simulation using just a capsim run and assign the results to a capacity matrix. And here it will give you a dictionary that we are using that here, using that to display as a data frame using pandas. And I determined the indices of each of these columns and index here in this capacity matrix by looking at the order of elements here on this side. So as a result of this, we obtained a capacity matrix that shows us the relations between different elements in your circuit layer. So we have 3 elements. One is the ground. You have the cloud coupler, and you have the exmon as a metal layer. So in order to get the shunted capacitance that we would like to have, we are looking at the self-capacitive element here. It's in this row, exmon to exmon, which is around 106 femtofarads. And based on our initial analysis with IC qubits, the equivalent capacitance for 180 EC was around 107 femtofarads. So this matrix in HFSS and here also is called Maxwell capacitance matrix. That shows the relation between each of these nodes and also the relation between the ground and the distant layer. So The diagonal elements of the capacitance matrix are representing, as I mentioned, the self-capacitance of components, and the off-diagonal elements represent the mutual capacitance between these components. So this capacitance matrix actually determines the main relation between the node voltages on your system and the charges. So for that, we can create a matrix for these three elements like this, where each capacitive element map one charge per voltage value here. So for the diagonal terms, for the self-capacitances, you have this relationship between only the node voltages and the node charges, but the mutual capacitances defined in terms of the difference between voltages on both sides. So this is the case for all diagonal elements. So there was one interesting thing actually nobody asked in this capacitance matrix. The question is why the self-capacitive matrix elements here are positive while the cross-capacitive matrix elements are negative in this simulation. The reason for that is actually how these capacitances are defined. As I mentioned, these are defined with respect to node voltages, and for non-diagonal elements, they are defined as the difference between two node voltages. So then, actually, if we write all these three charge to voltage relations and group all the terms that correspond to a particular voltage together. So let's group V1s and V2s and V3s. We can end up with an effective capacitance of the 1,1 term plus 1,2 term plus 1,3 term, while the -1,2 and -1,3 terms are coming from these actual differences. So actually, this maximum capacitance matrix you get from HFSS or you get from Palace are giving this effective capacitance matrix you have here. So here the 106 is actually a sum of its self-capacitance and the capacitance with respect to ground and Coulomb added to this value. So you can say here you have 68 between X1 and ground, and 16 between Coulomb and X1, which adds up and become 84. But our X1 self-capacitance is 106. The reason for that is because all of these eigenmodes, these EM solvers, are actually assuming there is a ground at infinity, and this X1 has an interaction with that. So this is an important point, and the result you get out of this capacitance matrix is actually enough for you to have all the shunt elements together. So you can use this to calculate your capacitance. So let's repeat this. So as a result of this, we got 106.33 femtofarad, and if you if you plug in this to your frequency formula, you will end up having a frequency close to 4.9 gigahertz, which we originally designed. And we can verify that with eigenmode simulations as well. You have one question?
Yeah, I wanted to ask, how do you relate these parameters to, for example, like the ABCD parameters that the power part we talked about this morning? Is like, do you directly take, for example, the claw and turn it into your parallel, into your series inductance capacitance? How do you add the shunt to the ground? Like, how do you make the connection?
Actually, that's true. You can create an equivalent circuit using this capacitance matrix elements. This is for a smaller scale device, but you can do that for actually much larger, much complex devices by defining different paths, different nodes to your different qubits, and you can check the capacitances between different parts. You can also define your pad and resonator a node, and also your qubit another node, and you can basically simulate your capacitance between two nodes. And you can plug that into a ABCD matrix. Actually, we will briefly talk about that, but ABCD matrix, the essence of the method is also obtaining the admittance, the resistance, basically seen by your qubit. Yeah. And you can do that at the terminal of your qubit, and that ends at this capacitance between Coulomb and your actually qubit itself.
Okay, so it's not necessarily taking, like you have to find ports in your system and then, or can you use the Maxwell?
You can do that, especially in HFSS. There are two methods of getting capacitor matrices. One is called Q3D extraction. That one basically does a similar job like this simulation, assigns nets to different metal pieces and checks at capacitances between them and also their self-capacitance with the ground. So you can get those values and directly plug that in, or you can define ports for your qubits where the junctions are supposed to be, and you can do what we call a driven model simulation. So basically, for each port, you can send small excitations and check the response of that at other ports. And that can give you an effective capacitance value between the system. So these are two complementary ways that you can use. Driven model, though, especially this is an X1, this only has one piece of metal, but most of the transmon you see are comprised of two actually metal pieces. If you use a driven model simulation for that, you would get the effective capacitance for your simulation. But if you use Q3D, you can get individual path capacitances as well. So depends on the detail that you want. You can have actually different simulations here. So we can also obtain the qubit frequency by doing an eigenmode simulation on the qubit. Although, in order to have an accurate estimate of your qubit frequency, you need to have a very high mesh density and very good convergence parameters, because eigenmode simulations are complex matrices that you need to solve and diagonalize, and there is often convergence issues, often precision issues with those simulations. So you need to be a bit more careful. So these capacitive models are very useful for constructing lumped element models like ABCD matrix. You can use that, or identifying your qubit as a circuit and diagonalizing that. These capacitive matrix simulations are very useful for that. But if you are interested in more complex behavior in your qubit, if you are interested in some loss mechanisms and stray interactions with distant qubits that you cannot simulate with your capacitive matrices, you can actually use eigenmode as an alternative method, which I will show you now. So here we do not initialize a new design. We are using the same design, and here we define an eigenmode simulation on top of that. Again, we have a similar type of user-defined options that shows the solver tolerance. Here we have actually these new parameters where you can ask your eigenmode simulator, the calculator, to have a starting frequency around 4 gigahertz. And you can determine how many frequencies, how many eigenvalues you wanted to find. So here we selected 4 gigahertz as a cutoff. For otherwise, if there are any other parasitic modes or any like a solver issues, you can get more parasitic modes as well. And I also restricted the number of solutions that I would like to get out of it. We are applying the same parameters that we are setting the same comments, similar to capacitor matrix simulation, for adding ground plane, adding the metallic layer. Also, we wanted to find mesh the bounded region inside the qubit. Here, as an extra, in order to accurately estimate our qubit frequency, we also simulate our Josephson junction as a lumped inductor. So basically, the port we put in place of Josephson junction, we assign an inductance value there so that our simulation can give us the right result. So after this, I would like to show you how the mesh looks like for this kind of devices and where you should be careful. Right, got broken. Do you have any questions, by the way, online? Just let's define our design again. Let's initialize our
Question.
mesh again.
So if you're grounding plates
Mhm.
of the resonator have holes in it, do you have any simulation for grounding plates with holes in it?
Between, could you repeat
Just
it?
inside them, like if I recall from yesterday.
Mhm.
Talk, there this design having like porous and grounding plate.
Yeah, I remember. Those are mostly actually to break any possible magnetic vortices inside your ground metal,
Yeah.
so that those don't affect and create flux noise on your qubit.
Mhm.
So any stray magnetic field would create noise on your qubit. So those are for that. For simulation, actually, that's a bit overkill because it's a ground layer where the field is much weaker at that point.
Mhm.
And simulating those small parameters will be actually very resource intensive. So you can simplify and not use them. But one important thing we will talk about is when you are simulating coplanar waveguide resonators, which basically divides the ground into two, you need to have a ground have zero voltage all over your circuit, all over around your circuit, so that you don't have any voltage fluctuations that cause problems. You need to add some bumps that are connected from another layer, or you need to add some air bridges that can equalize the voltage between both sides of coplanar waveguides. So that's one concern when you're doing design, that if there are any isolated patches of ground metals. For example, yesterday Professor Woldorf showed their design, and they had actually a bunch of layers crossing each other and dividing the ground plane into multiple pieces. So for that case, you need to actually connect them in your simulation as well for your accuracy of your results. Yeah, so let's look at how the mesh looks like here. You can zoom around it here. So this is how our device looks like right now. So especially the region around here, this is only shows the mesh on the metals right now, but the mesh between these metal layers are also important. So you need to have enough mesh elements, at least within this width, at least 3 to 5 elements, in order to get an accurate field profile from your simulation. And especially if you are adding ports, like the junction port we have here, you need to also ensure that these are well meshed. So this is, by the way, just your starting mesh in any simulation that you have. All the simulation tools, HFSS or Talus, will be using the starting mesh, and depends on the accuracy of the calculation, it will actually refine this, add more elements. So that's why actually the number of solver runs are very important to reach your particular convergence. If you cannot reach a particular convergence, I suggest you to add more steps so that this mesh can be refined more and more.
So can we decide where to mesh it more dense
Yes.
versus rare?
So in this code, what we did is, so using this Q geometry bounds function, I got my XMON component from design, get the bounding box around that, and I use this fine mesh in rectangle function here to assign a finer mesh, which has a minimum of 15 microns. And for junction, also, I did a similar treatment here, around these boundaries.
So you
Like
can
this.
select elements and then
Exactly.
mesh them.
So in HFSS or other like a graphical interface, EM solvers with graphical interfaces, you can actually select and assign different meshes. But in this case, we select an area and a boundary and assign different mesh to them.
Are you saying like you assign different meshes for different boundaries, like where different materials?
Different actual components, I would say.
Okay.
Different components have different aspect ratios. For example, if you like to include the effect of Josephson junction is a very small element which has a thickness around 70 to 200 nanometers average. So if you want to incorporate its effects on your simulation, you need to assign a special mesh to that. Otherwise, your solver may not do that itself, or it would take a lot of time. So we are doing this initial meshing to help simulation to converge faster.
Okay. Thank you.
So after this, sure.
So online does the, in order for the notebook and everything to run, does the notebook itself need to be the same folder as SQD metal installation directory?
It is not. It should be in the same. It should be in the same environment. Okay. And worst case, they can try to install using pip install SQD metal directly from this one. So everything is clear so far. So let's discuss about our results from eigenmode simulation. So I did this simulation for 4 elements already, with a minimum cutoff of 4 gigahertz for actually a lightly meshed system. So this simulation takes only actually 1 minute and 13 seconds. So actually the actual simulations take at least half an hour or longer, depends on your computer. But we can easily see that there is only one mode around 5.1 gigahertz with a relatively high Q. So one of the things you can check when you try to determine which mode given by your eigenmode solver is true or not, you can check the frequencies, whether they are close to your intentional value, and you can check its mode profile. So here, I looked at easily here, there are 3 parasitic modes, around 27 to 32 gigahertz, which are non-physical for our system. And here I looked at this one and I plotted its mode profile. And as we see, most of the electric field state is between the X-mode metal here and the ground. So this X-mode style qubits have a dipole, which is distributed between the floating metal and the ground around them. So you can check that for more complex structures to assign, to understand which eigennode belongs to which qubit in multi-qubit systems, or whether it belongs to a qubit or a resonator in your system. So we will be talking about more how we can use these results, how we can interpret eigenmode simulations. I think you might have heard about energy participation ratio method from Zlatko. So that's a useful method that goes in line with eigenmode simulations. So if you can go to highest possible convergence, actually eigenmode simulation can give you a lot of idea about your overall device parameters. Based on the energy distribution, you can estimate the unharmonicity of your system. You can estimate the coupling between 3-dot resonator or your qubit, or especially nowadays, this method is used a lot in coherence research. So you can use the amount of energy present in different parts of your circuit. You can use that information to calculate which elements in your circuit causes the most loss. We don't just have loss due to the coupling to the environment through resonator or stuff, but you also have interfaces. Eli showed today, I think also, the interfaces with air around the qubit, the metal interface with the substrate underneath, and all of these due to fabrication related reasons, they have some loss components. This can be due to some 2-level systems forming in between layers that interacts with your qubit. It can be for other reasons. It can have its own absorption, cause your microwave photons to be absorbed by your substrate. So there can be multiple reasons. And by checking at how much of your energy is distributed over these interfaces, you can actually use this information to estimate how is your qubit Q looks like. So that's another useful feature about this eigenmode simulation. So if there is no question, I would like to slowly move to transmon resonator systems.
Can you say a bit more about the gap? Like how was the gap, like Q and all of that?
Sure. So as we said, most of the energy is actually stored in between this gap, between this crossbone metal layer and the ground layer around. So if this gap is smaller, of course, like you would have a higher capacitance. So you can adjust capacitance based on the gap between that center metal layer and the ground. But there is also another caveat. If you have a very narrow gap, the effective field strength between this cross and the ground layer will be very high. And in physics, we know that all these two-level systems, we can estimate them as a dipole. And if you look at the general formulas about dipole interactions, it's proportional to the electric field strength that your dipole sees. So let's say we have a two-level system here, or anything, any node that causes loss. Stronger the mode field here, more coupling you have with that system, and that would cause higher decoherence. So basically, by engineering the electric field strength between this crossbone and the ground layer around that, you can control the amount of loss you have due to those fabrication or material-related loss channels. So the one way of doing this, while having enough capacitance, but still have a low enough electric field strength, is making the qubits larger and larger, which is a problem for scalability. So overall, as a rule of thumb, we can say that our qubit performance can increase with larger qubit sizes at the expense of scalability and the die size. So that's why it is a bit hard to make transmon-based or superconducting qubit quantum devices smaller and put more qubits per die. The main reason is this. Unless you make your material more pristine, your fabrication better, so that you can mitigate these losses, you cannot make it too small so that these electric fields are not high enough to cause you extra decoherence chance. So we discussed about how a single qubit looks like and how you can simulate and estimate its frequency. Now I would like to move on to a qubit resonator system. So Daniel did a great introduction to that yesterday, where under the approximation of under the rotating wave approximation, we can assume that total Hamiltonian of a resonator and qubit system as the energy of the qubit. Also, this sigma z means we are assuming that our qubit is only living between 0 and 1 state, which is total rho. But it's a good assumption for start. A resonator frequency dependent energy term for resonator, and this A dagger A gives you the number of photons present in your resonator. So the total energy of system is also dependent on that. And there is this interaction term. This interaction term represents the relation between your qubit and your resonator, and its strength is determined by this G. So in device design, what we want to control is mainly this G between so that we can control the coupling between qubit and resonator, and we can control our readout fidelity based on this. So if you this is called the James-Cummings Hamiltonian, and it has actually it has a very common solution. So when you solve this model exactly, it would result in following eigenenergies. The first eigenstate of this would give you half of your qubit energy, while the higher order states would give you a resonator energy at the total of resonator and qubit energies, here you can see it's perturbed by this term of delta square. Delta is the detuning between resonator and your qubit, which is a must for dispersive readout. And also there is a G dependent term here, and N is the number of qubits. So here I actually examined these eigenvalues using again SC qubits for two different regions. Again, we assume that our qubit frequency is at 4.9 gigahertz. What if we put our resonator on resonance with our qubit? How would the eigenvalues of your total system would look? So if you look at here, so the first element here is corresponds to your qubit frequency, where there is no photon. So the resonator is unpopulated and it's out of system. You have 2.45 to gigahertz, which is exactly half of our qubit frequency. And then the next two terms we have here is one is around 2.4, the other is around 2.5, which is pretty close to each other. So here, on top of our qubit, I also defined, so I defined a generic qubit with our qubit frequency. I defined an oscillator in this Hamiltonian. And I also defined an interaction with this interaction strength G. Here, all the units are in terms of gigahertz. So I selected hypothetical G of 50 megahertz between our qubit and resonator. If these two resonators, the qubit and resonator, is on resonance, what we see is actually corresponding to, with respect to this frequency, 2.45, we see two eigenvalues, which are 5 megahertz below and 5 megahertz above than qubit frequency. So this shows that when the qubit and resonator are on resonance, and if they have an interaction parameter of 50 megahertz, you see we call it rest state, the joint state formed due to the interaction. These two individual qubit and frequency resonator states will be hybridize each other. You will obtain two frequencies 50 megahertz above and below your actual qubit frequency. This is due to the interaction. These two energy eigenvalues of these two systems will undergo avoided crossing. And actually, by checking the difference between these two eigenvalues, we can understand the strength of interaction between these two. But this only holds when your qubit and resonator is on resonance. When you have your resonator at 1.1 gigahertz away from your qubit, this is basically what we use for dispersive readout. We intentionally detune our qubit from resonator, because when our qubit and resonator is on resonance, they will coherently transfer energy, so that while you can have a better idea about your qubit state, at the end your qubit state would be destroyed, because we are doing measurement on our resonator. So in order to do efficient readout, while we are preserving our qubit information, we are detuning our qubit by at least, as a rule of thumb, 1.2 gigahertz at least is enough. But there are actually different considerations regarding to the readout fidelity that you want. Also, the T1 limit, the lifetime limit of your qubit, is determined by its interaction with the external elements. So you will want your readout frequency to higher or lower, like a farther with respect to your qubit. So the theoretical rule of thumb is the detuning between your qubit and resonator should be much larger than your interaction strength G, at least 10 times or higher. So in this case, what we observe is actually, so I could run this by first making this 0. You can see one value is around 2.45, and the other eigenvalue we have, these are the first split states, are around 3.5. This corresponds to actually the eigenstates of your qubit and frequency in this James-Cummings basis. So these are unaltered, but when I just add here a 50 megahertz of interaction, what we observe is actually not a drastic splitting as we saw in the previous simulation, with it on resonance, we see a small shift at our frequency. So this is called dispersive shift, which is the determining parameter in order for you to distinguish the two states of the qubit based on your qubit resonance. So this dispersive shift is state dependent. So based on the state of your qubit, whether it's on excited state or in ground state, as here, it will cause a shift on your resonator frequency, and that's the main mechanism we use for readout. So this is something widely discussed in last 2 days.
Question.
Sure.
So in this simulation, can we see how much that differs by, like for ground state and the first excited state?
For the first one, sure. So both of them are within. So there is a small truncation error here because the resonator is at 4.9, but here, in order to calculate the frequency Q, I use the actual parameter that we calculated earlier. So it's around 4,902 megahertz. So there is a slight shift. It's not fully on resonance, but you can see they are pretty close.
So actually, I'm asking if we have your qubit in 0 or 1, right? And we have the same coupling.
Mhm.
So we differentiate that by the shift depends on which state the qubit is in, right?
Yes.
So can we like see how drastic that shift is when our qubit is in 0 versus 1?
I can show you this here. So actually, if you look at this Hamiltonian in dispersive region, you can see that actually this James Cummings Hamiltonian, if you diagonalize that under assumption, it reduces to this in terms of ladder operators. And so the designed frequency is here. This is the omega Q. And you have omega resonator here. When you have interaction between your qubit and resonator, actually both your qubit and resonator has the same amount of shift, which corresponds to chi.
Okay.
So the value we get here, the shift we get here, which is on the order of 3 megahertz item,
Okay.
it acts on both on your resonator, which is where the most of dispersive shift terminology is used for. For qubits, this is also state dependent, and you can understand that by this sigma z here. So chi times sigma z is actually state dependent. It becomes state dependent and changes your frequency by the same amount.
Right.
But we can add that to your qubit frequency and say that the effective frequency of your qubit is omega q plus chi. And that's also called as AC stack shift.
In one case, it'll be on the left to the qubit frequency, and in one case, it'll be on the right.
Yeah. So you can do that as well. So this dispersive shift is mainly dependent on your coupling strength, G. It's actually G squared divided by delta. This is not the valid formula. This is the most simplified version of this. Actually, your dispersive shift also depends on your anharmonicity of your qubit and other elements if you don't assume in rotating wave approximation. But as a rule of thumb, you can determine your chi using this formula as basic as possible. So you can change the detuning between your qubit and your resonator, which if you increase that, it causes a reduction in your chi, the dispersive shift. So that means if you have lower dispersive shift, you will be able to discriminate your qubit state less by looking at your resonator frequency, because that's the main form of readout. We are looking at the shift in frequency of the resonator. But so dispersive shift also means that you are strongly coupled to your qubit as well. And your resonator is also connected to outside world. I will show as actually a design based on that. So larger of your detuning is actually more your qubit is decoupled from your environment, but at the expense of your readout fidelity. It's basically if you, in order to measure something, in order to measure your device, you need to interact with it. And interaction means decoherence. If you want long-living qubits, you cannot interact with that. control and readout will be much higher. So this is a second biggest trade-off after EJ or EC when you can encounter during your device design. So you need to adjust your G and delta well in order to have an appropriate dispersive shift for your readout fidelity while preserving your lifetime. So as I said, this is only valid assuming the qubit levels are truncated, 0-1 state, and only valid also at low photon numbers in resonators. As Daniel showed, when you have more photons inside your resonator, actually there is interaction between these photons in resonator and the qubit, which causes this measurement-induced state transitions and leakages related to that. So let's draw a transmolar resonator system. So by the way, one more thing I would like to discuss here is you can control your dispersive shift in order to control your readout fidelity. But your readout fidelity is not only dependent on the shift for discrimination, but also it depends on how much information you can get out of your resonator. That is dependent on the decay rate of your resonator. It's called kappa. And having a higher kappa would help you to do faster readout so that you can obtain that information faster. But faster kappa means more interaction with the environment, also cause your qubit lifetime to drop drastically. So the amount of that drop is determined by this G, the coupling strength here. In order to have fast readout, you can still have a large kappa, but you can make your G minimum. You can reduce that as much as possible. Sure.
So is this where the concept of circuit depth comes in? Like you make a measurement and that will sort of depreciate they'll decay your qubit, and the more you keep doing that, beyond a point you won't be able to like do any measurement on this qubit. So
it is related to that. It's not the only concept. There are other things playing a role there, like the decoherence induced by your gates. Not just it is the decay, but there is also dephasing. But your ultimate limit is your qubit lifetime, T1. And you can control your qubit T1 actually by controlling your readout properties. And the best way of doing that is actually here you can employ ABCD matrix simulations to actually estimate how much of admittance, how much of impedance you see acting from looking at qubit size. And that mainly determines your lifetime limit.
how fast it decays.
Sure.
Is it accurate to think of kappa as the rate at which photons exit the resonator?
Yes, exactly. So as a rule of thumb, if you do a careful simulation about your readout fidelity, the state distinguishability versus your dispersive shift at kappa, another rule of thumb is you can use this 2 chi equals to kappa as a rule of thumb. So you can set your dispersive shift as half of your kappa that you want to set to get maximum state distinguishability. This mostly holds in most cases, for especially basic designs. There are some considerations, especially if you want to keep your T1 higher. If you don't worry about your readout time, you can have this ratio, smaller, so that your qubit lifetime can be different. But 2 chi equals to kappa is a good rule of thumb while designing your coupling strength and the resonator qubit decay. So in the context of superconducting devices, we are mostly using coplanar waveguides. And these are essentially transmission line resonators, where you based on the termination that you do, you have a resonant frequency. If you have a both sides of this resonator, if you terminate them open, you would have a lambda over 2 resonator, where the wavelength of your transition is actually equal 2 times the length of your resonator. And if you short one side of the resonator instead of having open, you would have a lambda over 4 coplanar waveguide resonator. which has a frequency 4 times of your couple length, so for your resonator length. So lambda over 4 resonators are very useful actually, especially if you are constrained by the size of the chip. So since they are shorter, you can cram them into smaller spaces. But here, for a basic assumption, we can use a lambda over 2 resonator. And a resonance frequency of a resonator like this would depend on, of course, its length, and also the effective permittivity of the of this resonator. The effective permittivity of the resonator, it is dependent on both the substrate underneath the metal and also the environment above the resonator as well. So mostly for a planar circuit, you have air on top of that. So in this case, the effective permittivity for silicon is around 11.45. And if you add air, assuming air and silicon contributes equally, which is not always the case, in order to get the accurate value, you need to simulate that. You can get 6.22 by getting the average of that and use that to estimate an approximate length for your desired frequency. So what this effective permittivity defines is actually it defines the phase velocity of the wave. So in order to have a resonance, you need to have integer multiples of 2 pi inside the resonator so that you can form a standing wave. So that's the reason. So this relation changes when you have open-ended or short-ended, but the same rule of thumb exists. You need to have a 2 pi phase total inside your system. So here, by using this formula and by using this assumption, I use 6.2 here. I calculated the approximate length of my resonator as 10 millimeters. We will see that this is not exactly true because this assumption only holds when you only have your resonator, only have your wavelength. Most of the time, in order to control the kappa of these resonators, we would love to terminate them with extra capacitances. Let's say you can use a finger capacitor at the end, you can just use the gap between two systems, where I can show, I think here. So this end termination here is just a 5 micron gap, but that also has its own, I think it's better if I show this in Gmesh. Open our Gmesh again. So we see here the open termination here is actually a very small gap on the order of this gap between both sides of the coplanar wavelength. This also has some capacitance here, and capacitance, if you convert that to impedance, it has an imaginary impedance value, which can correspond to a phase change. So when you want to calculate your most accurate resonance for your resonator analytically, you need to incorporate these kind of effects as well. So you need to get the equivalent phase for your capacitances at the end. Also here, so this structure is again our qubit coupled capacitor to the claw. So this claw and this capacitance also changes the phase relation of your resonator, would change your resonator frequency as well. So if you don't simulate with and without, you will have different values. So we have these meanders, and here we brought them close to another bus waveguide here. This bus waveguide is used to interact with this resonator and the qubit here. And the reason we did it this way, to have a finite capacitive coupling between these two lines, so that we can control the kappa of your resonator. Otherwise, if you don't have such a thing, the kappa of your resonator would be mostly limited by how much decay it has through the substrate and other things that
the resonator coupled port. So from the capacitor end here, the voltage of the resonator is maximum, so that it has a high capacitive coupling coefficient with this bus waveguide, which you can use to control the couple of your resonator. Although, please. Yeah.
You said that you needed to like include the end of the claw. Would you then simulate it with and without the claw? Then kind of takes the
Actually,
difference in capacitance to ground you get or something. Like
what
that.
we are doing is initially we do a simulation to estimate the resonator frequency without the claw to bring it as close as possible. But in order to determine your final resonance frequencies, you need to add your qubit pad at least part of it, and you need to add this capacitance here. So the capacitance between this pad and this resonator claw will affect your resonance frequency.
And that's then this effective capacitance that we saw in the ABC matrix analysis.
In a way, actually, ABCD matrix, you can use ABCD matrix to simulate this as well. You can create a ABCD matrix element for this capacitance. You can create an ABCD matrix element for this transmission line. Again, you can create an ABCD element for this coupling here, and you can simulate all of them in a chain.
Okay.
So ABCD matrix is actually a very handy method to simulate and verify your design against your simulation. You know, where to couple, how long this arm should be. So these things are easily can be deduced from your ABCD. Okay. So here, for this structure, also another important parameter for your resonator is its characteristic impedance. Characteristic impedance, I skipped it here, determines both the coupling strength. Here, this is the G formula between qubit and resonator in terms of the field strength. As you see, it depends on the EG over EC ratio. It depends on the capacitance between qubit and resonator with respect to the shunt capacitance of your qubit. And also it depends on the impedance of the resonator. So you can adjust the resonator impedance by playing with the ratio of the central conductor of your resonator to the gap between ground and your resonator. So higher in that impedance here would help you have a much higher actually G for a given capacitance. But also you have other implications in your system. Most of your microwave systems are operating at 50 ohm. And if you have a resonator or bus waveguide with impedance other than 50 ohm, you would have mismatch. And those impedance mismatches causes reflections and return loss in your system, in your microwave system. And that would cause a change in your kappa. Actually, if your difference between your impedance of your resonator and the environment is much different, your kappa would change a lot, and your qubit would end up having a much lower lifetime compared to what you desire. So determining that is also very important. So here for this purpose, so for this work, I use eigenmode simulation to determine the resonance frequencies of both qubit and resonator together. Again, similar to qubit, we use the similar parameters, the number of solutions, number of frequencies. You can also determine the number of CPUs you have. You can change the solver tolerance here. Different from the previous simulation, we added here CPW ports. These are added to the ends of those bus waveguides, and we intentionally covered those ports with 50 ohm terminations. This is not a must, but if you would like to get an accurate estimate of how much is your loss, how much is your T1 from eigenmode simulation, if you can get it converged well, you can actually extract that from eigenmode simulations as well. By adding a small lump resistance on your system in the form of port and do eigenmode simulation, you can actually have a loss estimate by looking at the field strength, the amount of energy stored on that pad, stored on your 50 ohm port termination, because that represents actually the coupling to the environment. The amount of energy that is stored over 50 ohm ports would give you an idea about how much energy is escaping to environment. So that's another good thing about eigenmode simulation, but converging it is also another story. So here, I think if you want to try this at home, Palace solvers are able to define this coplanar waveguide, this port and peak tone terminations on coplanar waveguides. But in eigenmode simulation, you cannot have any excitation source. So you need to shut off the excitation normally Palace is using to do other simulations like the driven simulations, terminal simulations in order to get S parameters. So here in this cell, we use this small snippet which loads the configuration file for simulation, deletes the excitation part, and reloads that in order to, this is a workaround for this, in order to do the simulation. So after we do this simulation, we get a bunch of modes with different frequencies here. Now it's actually more tricky to choose which one is which one. So the things you can look at in a well-converged simulation, you can look at the Qs of your mode. For like here we see there are relatively high Q modes at 4.84, which is close to our qubit frequency, and around 2.6 to 6.2 gigahertz, we have another high Q mode, which might correspond to our resonator frequency. And in order to double check that, I am looking at its electric field profile. So when I see here, this is the mode number 4, corresponds to 4.8 gigahertz mode. I see most of the energy is that electric field is stored between our X mode and the ground wave. So this is highly likely that it's the qubit mode. The reason why you have non-zero electric field strength on here is because our system is coupled, our qubit is coupled to resonator. So actually you can see the amount of coupling between your resonator and qubit by looking at eigenmode simulation. So that's why eigenmode simulations are very enticing in order to extract all circuit parameters at one, just one simulation. But making it very accurate requires a lot of resources in terms of computation. Any questions? Sure.
Yes, so if you want to set your qubit to 0, can we do it, and can you explain how we can do it?
If we set our qubit frequency to 0?
No, not the frequency, the state of the qubit. For example, if you want to run a quantum algorithm and you want the initial state to be 0.
Sure.
So how do we do it?
So the main way of doing that is what we call, actually, it's in the domain of reset. So you need to reset your qubit state, and there are different ways of doing that. So the first one is called passive reset. Basically, your qubit has a lifetime that's related to material losses, and also it's coupling to the resonator and to the environment. So in the passive reset, if you wait at least 3 to 5 times of your T1 of your qubit, if like a qubit is isolated, or like if you wait until the resonator 5 times the resonator kappa, for example, you can have all the photons escape the system, assuming that your system is cold, so you are at a very low temperature. There is no excitation that replaces that photon. So you can wait for a second at the beginning of your measurement, and then you can ensure that you have 0 state with high probability. Also, there are methods for active reset. Daniel talked about one of them yesterday. It is called multi-level reset. In that regime, you put your qubit frequency above your resonator, and you make your qubit tunable so that its maximum frequency is above the resonator that you operate with, but your minimum frequency is below your resonator. And you can calibrate a pulse scheme where you move your qubit frequency below your resonator within a given time period, and you can ensure that all the excitation that is lingering inside your qubit and resonator can slowly evacuate the system and thermalize to the environment. So this is one way. Of course, this only works when your qubit frequency is above your resonator frequency.
And how do you change that frequency, like these parameters to do?
So for that, we are not talking here, but you need an extra control element. So first thing you need to add, so I can go back to here. So you can construct a tunable transport by adding here, this was our circuit, assuming we have a single junction. You can add another Josephson junction parallel to this, which creates a loop, what we call a squid. It's a quantum interference device. And the effective inductance of this squid loop, it is determined by the magnetic flux that is passing through this loop. And for that, you can, let's say, create another strip line, another waveguide that comes nearby your qubit and shorted like nearby your qubit, so that there is a current passing according to the voltage you supply from your outside of your bridge. So that current would induce a magnetic field inside your loop and would change your external phi. And the change of frequency with respect to phi, we can simulate that with SC qubits here. So by adding this flux tunability on this, we are able to play here the maximum frequency 4.9. Here I intentionally added an asymmetry, so it doesn't go to 0 completely, but it goes somewhere around 3 gigahertz. You can put your resonator around 3.8, for example, gigahertz here. And when you increase the flux bias that you have, and you increase the voltage at your microwave port, you can have more current passing through here that would induce more external flux, and your frequency would go down. So that's how you control it. For that, you need to add an extra line coming in the vicinity of your qubit. Sure.
Just to make sure that the color there is the density of the energy density, maybe like the magnitude.
It's real part of the electric field. The
Real part of it. And is it also possible to plot the voltage and current on the conductors at every point?
You can. You can do current density, both in HFSS and also Palace. You can do that. So this SQD metal wrapper, I think it's fixed. It has it fixed to E field, but in Palace interface, actually, you can get all of it.
So you could get the voltage on every mesh point. That's like one.
Technically, you should be able. At least I'm sure that you can get the current density flowing over for a given mode. And voltage, I guess, I guess we can obtain that.
Question online. What are ways that we can test for noise in the circuit, and what would be ways to test noise limiting approaches?
I see. Good question. So there are different noise components here. So one of the things is charge noise, for example, which you can look at your charge dispersion, and you can do some estimations based on your system. There are actually some theoretical formulas based on some noise densities, assuming a white noise of charge, or assuming a Johnson noise in your system. You can model different kinds of noise for your system. Its effect on your T1 and T2 would be dependent on your charge dispersion value. You have also the flux noise. Obviously, if you have a tunable transform, you will have a mutual inductance between the squid loop that you have and the line that I used to add the pass current and create magnetic field. That's effectively represented by a mutual inductance. And strength of that mutual inductance will also control your susceptibility to flux noise. So your flux noise will basically depend upon your control line, how much filtering there is, because you cannot directly assume just a white noise there and modify your system, because you will have multiples of filters and attenuators in your system. So you can actually model all these independent contributors, and based on your susceptibility, and the susceptibility figures are for charge noise, it's charge dispersion. For flux noise, it is that mutual inductance between your control line and squid. Also, if you have a tunable transform, you have the slope of this curve, which gives you the flux sensitivity. So how much your qubit frequency changes with this external flux. You can actually convert all this information into models that represent your mind. So it's, I think, a too long of a topic to talk right now, but I can point you to some resources about that. Actually, end of this slide, there's a Krantz et al. That touches that a bit. This is a quantum engineers toolbox paper. It's very handy for this kind of modeling, but actually there are very complex models that help you estimate this. Okay. Here we looked at the mode distribution and saw that this mode 4 is 4.84, which is close to our desired frequency. It's pretty much close to what we wanted, and it has an energy concentrated in a qubit. And you have the mode 6, which is around 5.8 gigahertz. These are, as I said, representative values done over a low density of mesh and low convergence, very actually relaxed convergence parameters. So here you need to look at whether your resonator mode is really forming. As we talked, this is a lambda over 2 resonator, so it will have a standing wave and a particular electric field profile. So you will see that the voltage of lambda over 2 resonator will be highest at the open ends, whereas since it is open, the current will go to 0. And at the middle of the circuit, you will have the least amount of voltage, but your current will be maximum. So by looking at these profiles and by looking at your electric and magnetic field distribution, you can look and understand whether your mode is actually lambda over 2 or lambda over 2.
And can you explain why you get like this blue area on the top? That looks a bit like.
This is outside of the calculation regime, so it just assumes there's an I think an air padding around that.
And no, I meant like when you look at the meander, like if it's a fundamental mode of lambda over 2, you would expect it to look like I guess something like this, you know. Like if we should have just like one voltage node, antinode, like 2 voltage antinode and 1 voltage node.
That's true. It is the fact that here the resolution of the mesh and the convergence is low. It doesn't give you the fully correct result. That's the main reason. And yeah, also the number of pixels here are pretty low. I couldn't get it higher.
Yeah. And the rest of the modes that had low Q, like, do you know what they are and like, are you worried about them?
So I checked them one by one. You can take a look at some of them are caused by actually some of the higher frequencies are caused by this bus line you have here, and some of them are parasitics caused by like a flow itself or some other state interactions. It's just how eigenmode solver is converging.
And what does it mean that they have low Q? Like how can you...
Low Q mostly identified, they are not physical. Having low Q or having like a imaginary side, the imaginary side of this shows you actually the amount of decay at that particular frequency. So if those are, for example, the positive values here might show you it's not a physical value, because that means based on the formula of kappa, that means not a decaying circuit, but instead it's like an active circuit with increasing amplitude. So those kind of evidences are enough for you to distinguish between different states. Also, one last thing is you can check the participation ratios, which just I will talk now before closing up. I think we have almost the time. So here, actually, based on looking at this mode dispersion, as we discussed before, we can learn a lot of things. And one of these handy methods are called energy participation ratio, which is the ratio of energy stored in a particular element, ratio of that to the total energy stored in this particular element. So this energy concentration shows you what part of your device for that particular energy has the most energy density. So that would show you where your resonance is. And also, if you carefully look at the participation ratio at your junctions for different modes, you can see how much your junction is coupled to those individual modes. And that can give you an idea about the unharmonicities or those dispersive shifts and couplings in your system. So actually, you can learn a lot by modeling your junction in your eigenmode simulation and looking at how different modes interact with them. Even sometimes on a large-scale simulation, when you have a mode which is distant from junction, it might have some coupling that causes energy stored on that junction, and you can actually understand about your state couplings. So here I come up with the participation ratios of this. Here we can see the mode 4 and mode 6, which has the highest actually in terms of indices. It's like a 0, 1, 2, 3, 4, has the highest participation ratio. These participation ratios are in terms of the energy stored in junction. So for each of these modes, we are looking at how much junction is interacting with that particular mode. So, and based on that, I assign my values to mode 4 to qubit and mode 6 to cavity. And when I calculate this participation ratio, as I said, the participation ratio is just the ratio of energies. I get 22, this is not normalized, for qubit and 0.5 for the cavity. So if you use HFSS together with Qiskit method, there is an interface that does all of these for you, that can take all the resonant mode frequencies and their mode profiles and calculate all of these energies in the form of integrals. But in the Palace, we decided to do that separately, analytically, because there is not a clear actual connection between these two packages yet. But it's also a good exercise for us to see how we can obtain different important circuit parameters from participation ratios. So here we first normalize them with respect to the total energy, so that the amount of energy you can understand how it's distributed as a percentages. So here, for example, for the qubit unharmonicity, we are looking at the participation ratio on the qubit and multiply that by square of our qubit energy and divide that by EJ to get the unharmonicity, the self nonlinearity of our qubit itself. So sometimes you will hear in this context, people will talk about self-Kerr and cross-Kerr terms. Those are these nonlinear interaction terms. And cross-Kerr terms are basically the dispersive shifts caused by coupling between different components. It's not actually a term that is defined between qubit and resonator. It can be defined between two different qubits, qubit and coupler, or different terms. And self-Kerr is mainly the unharmonicity. You would expect the unharmonicity of a resonator is very small, while a qubit is highly nonlinear because we intentionally do that. So here, same thing, we do that for resonator unharmonicity. For the cross-Kerr term, we multiply, cross-Kerr term is basically a dispersive shift. We multiply the participation ratios of both cavity and qubit and include the omega qubit and omega resonator here as well. So actually, these are a bit agnostic terms to define couplings between different resonances in terms of this energy distribution. So in that case, it's actually a very handy tool to calculate different parts of your system properties. So here I summarized most of them. So because the simulation is not well converged, the actual qubit unharmonicity is not 180 megahertz, but instead we are getting it close to 155 megahertz. We get a relatively large dispersive shift again when you have, so as I said, in order to have the most accurate parameters for this, you need to have a very high convergence. The one thing participation ratio and eigenmode simulations fails the most is actually calculating this effective interactions. So that's why I will briefly talk about a way of getting these values from capacitor matrix itself as well. So if you can converge your eigenmode simulations really well, you would get values that will be pretty close to your circuit parameters. But if you cannot, you can also extract this based on lump element approximations. So I don't want to go too much on coupling two transforms. I think like it's been 2 hours now. But one thing I would like to show you is this, which is often overlooked. So any coupling between two different elements of your circuit, whether it is qubits, whether it is coupler, whether it is resonator, can be identified as a normalized coupling parameter. So this normalization is done here. I am working on a two coupled qubit system, which have their paths are directly interacting capacitively between each other. So its circuit diagram looks like this. And we are interested in how much these two qubits are coupled to each other. So for this purpose, we are doing a capacitor matrix simulation. And as a result of that, we got, for the self-capacitance of these two exponents, we are getting 97 femtofarads. And there is a interaction capacitance here around 4 femtofarads, which causes a resonant interaction if the two qubit frequencies are the same. This is one of the ways you can create an exchange interaction like a swap gate between two qubits. So the strength of this interaction, you can identify that in terms of unitless coupling efficiencies. So here it is CG divided by the square root of these two capacitances. Basically, we are getting the geometric average for these two self-capacitances. And take the ratio of that with respect to this coupling capacitance to get our coupling efficiency. So you can do the same calculation using eigenmodes and see that how much the energy of mode 1 is coupled to the junction on the qubit 2. You can check it from participation matrix, participation ratio simulation. But the coupling efficiency here, based on this, we can get around like a 4.25% of coupling efficiency. And we can use this basic formula to estimate our actual G strength between two qubits. So it is the basic formula, it is the K times the unitless coupling efficiency times the geometric mean of these two frequencies of interaction for two qubits. So it is basically here, these are on the resonance, FQ1 and FQ2, divided by 2. So assuming that your two qubits are on the resonance or near resonance, you can have a basic estimate about your coupling strength between two structures. Of course, when you have large detuning between two systems, you need to modify this and scale by the ratio of those two frequencies. So that's a scaling parameter to your G. But for two resonance systems, by using your capacitor matrix, you can get to the G element you would like to use in your Hamiltonian simulation. So I would like to stop here. For your benefit, I actually put some references that I found pretty useful while I was working in this field for a while. This field, unfortunately, for conducting device design, there is not really a canonical book that everybody can consult to, but there are very good review articles that you can look at and understand more about this. Actually, one of our organizers, Eli Labasov, recently wrote a paper about design concerns. What should you look at when you're constructing your actual layout? So that might be pretty useful. And to learn more about the physics and other concerns about these devices, I would suggest you to have this Alexandre Blay or Yvonne Gao or Kranz et al. Here. And one more, maybe this Rasmussen et al. It has an explanation of how this circuit quantization and Hamiltonian calculation methods work, how you can construct, using knobs and fluxes, you can construct Hamiltonian of your circuit. So you can look at that if you want to learn more about this field. So you don't have to tie to any of these formulas or methods. There are multiple ways of doing this, but the underlying calculation methods are mostly the same. So again, thank you for bearing with me for these 2 hours. I know it was exhaustive, but I hope you have a better idea about how a design workflow looks like for small scale devices. So thank you again.